Okay, good morning, everybody, and welcome to our fourth day of the online training webinar. Today, we will be talking to you about the PID on the IDEC FC6A series. This topic probably needs about 3-4 hours to do a fair job of covering it. We committed like 1 hour just so everybody will try our best to do a good job on it, to try to hopefully explain it, highlight the most important parts and components of it and how to demonstrate it. We will use a live example. I will introduce myself. My name is Elias Alters, and I'm reporting to you from the beautiful state of Arizona this morning. And I will be going over the PID on the FC6A. And again, we're going to do a basically live demonstration, so kind of explain how the PID works on the FC6A, how do you set it up, how you configure it, how you set it up, how to work with it, to give you at the end of the seminar a hopefully give you the enough knowledge you can apply it on future project and be comfortable with it. The PID, I will go over a quick overview of the PID, what it is, but due to the complexity of the topic, I will not go in a lot of details. Again, this really meant the way we came up with this schedule. The PID was meant for longer sessions, but we decided to do like 1 hour sessions because we know a lot of you are staying home, but you're working on so many different projects, and you're basically we thought the 1 hour slots are the best way to do this. So I'll start for those of you who are new to PID. And also I want to add something. It seems like oftentimes we're getting a variety of attendees, background and level. It's really hard in this kind of settings to to get a group of people of the same level. So we'll do our best, as I said, to cover the basic to advanced aspect of the PID. For this new today, PID is a proportional integral derivative. It's a loop mechanism basically used to control process in order to achieve desired output, desired end. It's really intended for a safe, stable, reliable, and efficient process control. The PID, it monitors a process system and determines an output to control the process to a desired system set point. It utilizes a wide range of process control applications, right? That's what PID is. It's the graph I'm showing you this morning. It shows a closed loop where you have the gain, the proportional term, or gain, the integral term, the derivative term. You have the error, and then you every scan time you look at the error and you adjust your output accordingly to make sure the set point and your process variable are equal, basically. So really quick, some terminology. PID is a proportional gain. The I is an integral, the D is a derivative, SP is a set point, PV is a process variable. By the way, if you think, again, I'm going because it's such complex topic, guys, we will make all the material available to you, the example, the material we will use today. We will make it available to you on our website, and you will get a, when you sign up, you get link to our video conference, you get access to our presentation, our program demonstration. So because I have to repeat that because some of you may wonder why, I mean, there's a lot of information to process. Okay, so MV is a manipulated variable, or the PID output. The PID we will go over. It's going to be the PIDD with the extra D. Stands for derivative decay. So that's a special PID, or the newest PID added, IDEC added to the FC6A. And you will see new terminology you may not see in the older version of PID. The PV upper and lower volume, those are things you can determine. You get the SP upper and lower volume. You get the SP set point high and low. You get the MV limit high and low as well. And you get the error. And hopefully everybody who had any experience with PID realizes that the error is nothing but the difference between the set point and the process variable in both acting and and reverse acting or regular acting. So, but as terminology, you will see again, reverse acting, basically the controller output decreases with an increase in PV, right? It's the opposite of the direction, right? Direct acting, the controller will go in the same direction as the PV is. You want to increase the PV, you want to increase the output, you want to decrease the PV, you want to decrease the output. In this PID, you will see in a second, you can run in manual mode, auto mode, or cascade mode. I'll explain that. Auto mode is when you control the output of the PID, not the logic. You are in control of it. The auto mode is when the system is taking care of itself. Now, the auto mode is not the same as auto tuning. Those are two separate. Auto tuning is where you tell the system to auto tune your application. Auto mode is you are tuning, watching it, and changing the parameters, but the system, is relying on your inputs, on PID parameter inputs to tune itself, basically. And the cascade control is basically the SP is provided by the remote set point. So I'll show you a picture of that in a second. This PID, part of PID, guys, it does, of course, has all the bells and whistles of an advanced PID control. It got bumpless transfer, which the controller output will not bump during transition to different controller mode. You got the anti-reset wind-up, very, very important. The anti-reset wind-up is when the controller is based on the integration of the error, is always limited 0 to 100%. So it does not wind in uncharted territory. It's always going from 0 to 100% to limit, to limit any winding and stuff like that. Derivative decays, it slows down the derivative response, which if you, in case like that, you want to apply that. And then you got the inhibit. The inhibit is when the controller operation, it's not in manual mode, right? When the controller is not in manual mode, the controller MV will track basically the MV input parameter register. If the minute you put the controller in manual mode, the controller immediately will disable the inhibit of the controller. This is another couple of really important formula you can look at later, try to understand what goes behind the, inside this controller. You get the MV, that's your PID output or manipulated variable. It's notice you have two important state, what we call the dependent or algorithm, that what goes in the dependent and independent. In the dependent, guys, the KP, which is again affects the error, the integration of the integration of the error and the derivative, right? So it affects everything. In independent, the gain only affects the error. It does not, the gain does not have any, does not get multiplied by the integral or the derivative term, basically. KP, we talked about that, the controller gain. The KI is, we already described that, and the integral reset, some people refer to as a reset. And in this algorithm, in the KI, guys, is repeats per minute. So when you are trying to tune it yourself, it's how you're going to think about whatever value you put in there, that's repeats per minute. This is what you're telling the controller to do. This some really cool feature we talked to you about. What's I mentioned, some of you are familiar with our old PID. So basically, in our old PID, we got the almost similar, of course, settings, except it's the main difference between the two are the PIDD is a little bit a better written algorithm, more advanced, and it uses a floating point versus whole number only. Like the old PID, some of you are familiar with, it only uses like 0 to 65, 535. You cannot, if you're doing precise PID, you cannot do a fraction of a pressure or fraction of a temperature changes. So it's only whole number. In the PID, you get the floating point control parameter. You get cooling and heating control. Of course, you can do both. You get the bumpless transfer built-in derivative decay. You get the anti-reset wind up, the cascade option, and you can do up to 32 control loops. And you got, of course, the interactive. I like that. This is we added to everything else. Number 8, your interactive PID monitor table and PID monitor setting box. So basically, that's what I will get to that. So basically, that's what I'm talking about. The GUI you get in a monitor mode. So once you begin to turn the PID on and you begin to tune it, you can sit down and monitor the behavior of the PID of your system. You can monitor it's color coded. You can change the color. You can monitor the process variable. Of course, that's your input to the PID. You can monitor your set point. You can monitor your manipulated variable as well, right? And then you have access to this, the menu down there to a lot of different parameters you can go and access. And you can change your gain, your integral, your derivative. You can go from manual to auto and so forth. You have access and control over everything, guys. And I thought I'll give you again a quick, really good idea to kind of give you a quick look at what happened in PID loop. I chose a pressure transducer or basically or a tank where we're monitoring the pressure and we're outputting to a pump. We have a valve and pump basically to maintain pressure level, whatever you want to call it. So notice this would be your process variable, the output from the pressure transducer or the level sensor. And then you get the set point, you get the manipulated variable, that's your output, right? So basically the PID will send an output to pump more or less liquid, water, or whatever it is to maintain the desired pressure in that tank. So if you have more usage of that tank, of course, the PID is sending more flow into that tank to maintain pressure. That's all what it is. Really quick, the cascade, because that's kind of a quick pick at the cascade. The cascade, guys, is almost similar, the same concept, except now you have two interconnected loops. The first loop is the same thing. You're taking the pressure transducer or signal level, and then now you have the process variable, you have the set point, and the PID output of the first PID loop becomes the set point of the second loop. Basically, that's what goes on. What you have the inner loop, it gives you like 3 times faster than the first loop. And finally, the last thing I will do before I jump into this is show you dependent versus independent. Independent, guys, you can see that 1% error, and you can see the effect on the PID CO output or PID output is 2% error. Look, so this is why we cannot recommend the dependent versus independent is the reaction of the PID output. So this shows you the time versus the PID output or controller output. Independent, you get a lot more reaction versus dependent. Just keep that in mind. You can look at that later. Okay, guys. Now, if I may, just want to tell you, of course, we're using this FC6A PLC for this example. I'm using IDEC FC6A. You can use any FC680 PIDD. And to do the demo, some of you, I'm using one of our training demo because I'm basically sheltering at home, and I didn't have access to more sophisticated system to do the demonstration on the PID, right? So what I'm using, guys, I'm using our training demo. In this training demo, really quick, I have a PID box, enclosed box, with a K-type thermocouple and a heater and a cooling fan. That is the box I'm going to use to demonstrate the PID for you this morning. This is the rest. Don't worry about this. I'm not going to use any of that. Just I have a K-type thermocouple you can see on the right-hand side. The first part of it, guys, is going to be a repeat of what Mr. Britt Davis covered on the first day when he did the scaling. I'm not going to repeat that because, well, if you did not attend that, I'll just really quickly mention it. But you can go watch the video if you want to see how we can scale the K-type. So I'm going to take that K-type thermocouple when I start the demonstration. That's day number 2, or March 24. You can go watch that video. I'm going to show you really quickly. I'm not going to go over detail. Britt Davis did that. Show you how to take this K-type, scale it. That's going to be my PV, my PID PV or process variable. Take it into the PID box, to the PLC. And then my PID output, guys, is going to the heater. So I'm going to set desired temperature inside that box. And I'm going to measure the temperature and change the temperature inside that room. Let's say you're, I don't know, you're breeding or raising shrimp in that box or something. You want to maintain perfect temperature. I mean, think about it that way, because that's the best I can demonstrate. Okay. Now the PID output, guys, again, is I'm gonna take I don't know if somebody noticed. Everybody knows the PID output is a data register variable. I'm gonna go take that variable and pulse that heater because that's an on-off heater. Pulse it to decrease the temperature inside that box. Now, the heat gets trapped in that box. So to create like a reasonable example, guys, I use the cooling fan. I'm gonna control the cooling fan to create a load on that PID. Okay, so that's it. So really quick, my process variable is a K-type thermocouple into that PLC, and then my output is a data register. I'm gonna go and use it to pulse that heater, and I'm gonna use a cooling fan to create a load. So let's go ahead and I'm gonna go to the WinLadder software. And for some of you who are joining for the first time, the PID, of course, I'm gonna use a PLC programming software. That's WinLDR, and it is part of many tools in the automation organizer, which you can get as a courtesy of joining this seminar. You will get access to a free copy if you like to. That's explained in the email you got from Aida. So let's go ahead and launch the WinLDR software to demonstrate the PID. And this is basically my WinLDR software. For those of you who are, again, may have 1 or 2 people, hopefully not new to PID or new to IDEC, just so you know, the IDEC software, the WinLDR that I'm using. So I just have the PLC. Basically, I went and assigned an IP for it, 192.168.112, so I can communicate with it. There are 2 Ethernet ports. And some of you, again, if you think eventually at the end, say, oh, wow, that went really fast. Okay, guys, because again, please hear me out. If you were not on our training webinars, which we launched this week, starting on Monday, the 23rd of March, Mr. Britt Davis, my counterpart out of Cincinnati, Ohio, covered the first part. I'm gonna go over really quick. If you want more to sit down and learn it better, please refer to our recorded webinar available to you through the link you got from Aida. So back to my basically I'm not gonna go over it. I'm using what Britt Davis showed you. So basically, I'm showing you how to configure. I'm taking the K-type thermocouple. I think actually that also was covered yesterday for the data logging by Rich Kirk, when Mr. Rich Kirk out of the East Coast, he also covered that. So, but anyway, for details, you can refer to those presentation, recorded webinar. So guys, the K-type thermocouple, which I'm showing here, coming to my analog card in the PLC, is what I'm going to use into the into my PID for my application, right? So I'm taking the K-type. I want to express in degree Fahrenheit, right? We did that before, right? And then I converted, because coming as an integer, right? Converted to floating, put it in the 1100, and then I divided by 10 to get the basically to get the floating. Remember, PIDD requires floating data. I can't use it. I mean, it allows you to, so I can basically tune this application, guys, to a 10th of a degree or a 20th of a degree or what have you, right? So it gives you all the accuracy that you can benefit from and so forth, right? So now, so this is already covered again, right? So now, I'll start this, you know, so I want to start this over. I can do it from scratch. So this is what, so I'll go ahead and delete this. So we'll do it together, so you don't feel like so you can see how it's done. So I'm gonna go to the home tab, grab a normally open contact. Now, again, for the sake of time, I want to always have the PID open, right? I want to always have the PID enabled. So I'm gonna go grab a normally open contact and program M8125. It's again, in the previous webinar, if you go listen to them, there are more explanation. I'm using an always in operation, always true bit, because the minute I turn the system, I want it to go to PID. I want to enable the PID, so I use an always on. Now, under advanced instruction, guys, you go. I want to go grab a PID block, right? Go to advanced and go to PID instruction. And then notice, which I described in the beginning of this webinar, guys, that's, and some people say, oh, well, this is kind of confusing, that, well, how come there's so many? Not really, guys, because remember, first of all, the first one, PID control FC5A. This is a very old one that we have to keep it there because that's the only thing what was available on our older series, right? And WinLDR, it's been out for 20 years, so it covered our old generation or legacy PLC. And then you get the PIDA and PIDD. I chose to go over PIDD because it's a better algorithm, more advanced and more capable. And for the simple reason I mentioned, it's got all the bells and whistles, including the floating values that allows you to control in a fraction of a point of a PSI, or fraction of a degree, or a fraction of a pH change, whatever you're controlling. So I'm going to choose the PIDD. PIDA works, it's fine too. I prefer the PIDD. So, and that's what IDEC encourage our customer to use the PIDD instead of the PID. Let's go ahead and double click on it, guys. So basically, guys, the control registers. Okay, so like what we did in previous webinar, you have to choose a register, any register right now that's available to your PLC. You can go and say, I want to go click on which register. You can choose any register from 0 to 200,000, basically, with the standard or the advanced registers. We have that. This PLC has 250,000 data register, 250,000 data register. Please keep in mind that the PIDD uses 100 data register, 100 data register. So I'm going to start at D4000 because the data I've already done. You can go with D0, you can go with D1000, right? Because I'm not very fast typer like Britt Davis is. So I'm going to just I already kind of labeled this. So I put PIDD control register, there are 100 of them to remind you. And the software tells you, I'll show you in a second, that those are used. If you don't remember, that's a very big problem. Initialize input. How do you initialize that? This is very important, guys, because why is this important? For the sake of time, I want to put M8120, which is, again, we went over in previous webinar in the data conversion. It's a special internal bit. I want to automatically initialize this. But in reality, really, I should put, let's say, M400, let's say, or M300, or M0, whatever. I can put any M bit here to initialize this. The thing with the initialize, this is to initialize the PIDD, right? To initialize the PIDD. Now you know what I'm talking about. And then the control relay. There are 28 memory bits. There are 28 memory bits available for this. So I'm gonna say, let's say start at M4000, just like to PIDD control relay. There are 28 of them. Okay, guys. So M0 actually, the M0. The reason I'm telling you, you can put an automatic initialization, or you can put a bit you can initialize, because whatever initial setting you put in there when you do when you go to the tuning, and then you do that, whatever you put in there, when you hit the initialize, it's gonna load those again, right? It's gonna load those again. So sometimes people want to revert to the original setting, they may have to do that, right? So that's what I'm showing you the difference between. So you can either choose to, but for the sake of time, I want to put in automatic. I don't want to go and do it. I want to automatically to initialize my PID. All right. So I choose the data register for the PIDD that is gonna consume or map 100 data register. I'm gonna use initialize pools, either manually initialize or through the HMI, or it automatically initialize it. And then a control relay. This is to allow you to change from state to another state, to do all the state changes automatically, right? And then into that. So let's go to the control setup. Okay. So now the control setup, you could choose to basically, guys, choose the PID from. I could have chosen the PID. Say I'm gonna come from the first expansion card on the PLC, right? And then say that's analog number 1. I can do it that way. But since because this is, then in this case, I would have to change the upper and lower range value. In this case, I already had, in previous example, configured the K-type thermocouple, and I expressed it in degree Fahrenheit in 1/10 of a degree. Then I'm just going to use it as a finished product to be my process variable. What is my finished product? It's true temperature, the system temperature, let's say, and it's already in floating. So my data register for the PIDD, it's D1102. I'm gonna just go ahead and write it down. Now, so guys, as you know, in the K-type thermocouple, if you attended our earlier webinar, K-type has a range of like 27 degrees Fahrenheit, right? So let's say, this is the beauty about the upper and lower range values, guys. It'll allow you, even though you have a sensor that covers wide range of wide range. Let me show you what I'm talking about here. Let me click OK here for 1 second, so I make sure everybody with me. So look, the K-type, as you can see, guys, the K-type goes from -328 to 2300 degree, right? So the range of the sensor is 2700 degree, right? 2700 degree. So 1% error would translate into 27 degree. But in my application, let's say you're doing this PID, right? Let's say you're doing this PID on you're doing this PID on the to prepare, let's say, you're doing plastic molding, you're doing, you're processing chicken soup. The cool thing about it, guys, the cool thing about this is, you don't need to worry about going the full range, right? You don't have to worry about the full range of it. You don't have to go buy expensive sensor. That's what I'm talking about. You can go with the K-type, which even though it has 27-degree range, you can say, look, I want to really, I'm doing, let's say, in this, I'm doing climate control. I'm not going to go to 0 degree Fahrenheit. I wanted to go, let's say, from 55 degree to maybe 105 degree. That's the upper and lower range. So now that makes me, even though I have a K-type thermocouple, I can adjust the upper and lower to the climate, to the application I'm using it for. Does that make sense? So now I have 105, right? The upper range, the lower range is 55. That's what I want to stick with. In that's, let's say if you're doing the plastic molding, maybe you're gonna go from 100 degree to 800 degree. So it's still better than a range from negative 300 degree to 2000 degree. That's you. I highly recommend, even you're using pressure sensor, to limit that. This what helps you limit your application to a reasonable rational range you're using for. Okay, so now I want to let the set point. I will let the user change the set point from 0 to. I live in Phoenix, so 90 degrees is a nice day. So I'm gonna say allow you to change it from 0 to 90 degree. Let's see. Go ahead. That's 90. Not 0. I'm gonna let you change it between. Some people like it really cold, so I'll go 65. And then when I turn the system on, I want it to start at 79. So, okay, by the way, I skipped under control. I want the default to be auto mode. I have reverse control action, and then I have dependent as a type of PIDD I'm using. Okay, and then I said you can limit your set point so you don't have somebody put in 150 degree as a desired set point. You don't want that to happen. So you can limit that in your upper and lower, high and low limit. By the way, all these guys, all this, you have access to them in an HMI. You can, or from an app or from your monitor. Now, moving on to the output of the PIDD, guys. The output, I don't recommend you change this, guys. 0 to 100% is good because it's gonna take the PID output, whatever it is, and it expresses it in 0 to 100% range, right? Floating, right? So you can go to 62.225. I mean, it's plenty of resolution. Now, if I had an analog value, I can tell the PID to take, it'll automatically take my PID output, right, and send it to the data register, guys. So let me repeat that. If I don't have an analog output in this example. I have heater I'm controlling that. SLR controlling heater. If I had an analog output going to a variable gas valve, I would use data register, right? And then I would use that would be my PIDD out. That would be the output to the analog card going to, let's say, to the variable valve, right? They're controlling the variable valve or the whatever element, maybe VFD if you're doing water application. I mean pumping application. So right now I don't have an analog value. I have a digital output value. Now I say I want you to go to a digital output value, right? Which is in this case, it'll automatically, because I started with M4000, right? It's gonna go to M4016, the 16th bit, if you may, or the 15th bit of the register, memory bit register. So again, because I want to drive digital output a heat element. I'm gonna let it go. The software automatically is gonna give me M4016 to be the PID digital output, if you may. It's in memory bit, right? Because we don't know what you are going to do with this. So you maybe send it over communication through a communication setup. So either gives it to you as a memory bit. That is a digital output that's going to translate into this 0 to 100%. Let's go ahead and go to the tuning now. So in the tuning, you get all this. You can disable. I'm gonna enable the KD derivative, even though I go with very little derivative. I want to enable the also the DK. Again, this is, and I want to enable the PV tracking, right? Because when I run in manual, that kind of helps me. Now, here where you can go start with to initialize. This is your PIDD parameter. This is probably the most important part of this training. How do you choose your gain, your integral, and derivative? That's really the $1 million question, what we say in America, right? So the gain, guys, the gain is basically when you basically you can either guys you put 0.01, that's what gets multiplied by the error, right? That's the number that gets multiplied by the error. And I always recommend start with small gain. Start with small gain. I'm gonna start like with 3.5, right? Why? Honestly, based on experience with this, based on your experience, this is very reasonable number. You can, if you go very high, you risk of getting very choppy PID control, and it may overshoot in your case. So, and if you go very low, I mean, you risk of having very small reaction. Now, the integral, guys, remember, this is how many repeat or reset per minute that I does it. I like to do that about 5 times a minute. So I'm gonna go with about 12. So that's that. If I go with 12 repeat per minute, right? Then I'm telling the system to reset every 5 seconds. That's kind of reasonable. Again, based on experience. I'm gonna start with very small derivative, right? Derivative is just in second. So I'm gonna start with 0.01. That's good enough, really. That's if you can have very small. Okay, so that's it. So I have 3.5 gain, 12 or 5 repeat per second for the integral, and then very small derivative. I chose D1102 to be my process variable. I have limited, because the K-type, guys, I'm using a K-type. It has 2,700 degree, and I'm using this to control the climate inside the box. Then I limit that to within the operating range of my application, which helps you use any sensor and have very nice. And then again, my PID output is going to the 4000, the memory bit, which is 4016, right? Click OK, please. And then, okay, so we're done with the PID. Now, again, since let me go back, show you what, since my PID output, sorry, since I'm, that's really what I'm controlling inside this box, guys. And I'm gonna measure the temperature into that K-type coming into that probe right here, and then I'm gonna basically maintain desired temperature inside this box. So if I put, let's say, 84 degree, and the default right now is room temperature maybe 76, 78. If I put 84, the PID is gonna turn the heater on that you can't see inside this box. And then the heat will rise up. But since to have a live demo, I don't really have, there's no way I can exchange heat with the outside world very efficiently. So I would have to use a load, apply a load to that. And in this case, the load in this case is my cooling fan to try to interfere with the process, if you may, right? So that's basically what I'm doing. So let me go ahead and show you how that works. So this is the PID digital output coming, as you know, coming from here, right? This is this guy. M is a memory bit M4016. So I'm taking M4016, right? And then I grab an output, right, to write to the heater, the PIDD heater, which is Q5. That is the output and the PLC controlling that heater I just showed you. Now, I don't really need this. It's just to tell me when the heater is on and off, because I can, this is a small LED, demo heater LED, because I can't see the heater is on and off. Okay, guys? And now what I did, this really, let me split this wrong. I'm gonna come here, show you what I'm doing here. Really, this is what I'm doing, guys. This wrong, this is really, it's adding a load on my PID controls, right? Because this is adding a load. What does that mean by adding a load? Is basically this gonna add a load to my PID control. I'm creating the load. I'm saying when the heater is on, it's not on, I want to run the cooling fan. This is just a cooling fan, right? Like this is a box, the box, PID box, if you want, PID box cooling fan, right? This is a cooling fan. So why do you need that, guys? Because there's no way I can wait till I change for this to create a reasonable application. There's no reasonable, you know, I mean, I really have to create a load on the PID so I can basically do that, right? To create a reasonable, really demonstrable PID application. Okay, so this just create a load to basically induce cool air so that the PID will continue to in real time. Of course, you know, your application, you're probably pumping or heating or something like that. You already have the material, whatever, or the environment to create the load. I don't have a load on that. Okay, guys. So I'm gonna go ahead and let me save this, whatever save as. I'll just save this project. Just come to PID and then save it. Then I'm ready to download it to the PLC, right, guys? So hopefully everybody remember this. So I'm using my Ethernet. That's IP number 12. So I'm gonna make sure this is IP number 12, right? I mean, and then I'm gonna go to the setup. Remember, I think we talked, Britt talked about that too on the second day recorded webinar. You can download using really serial Ethernet or USB. You can use USB, I can use serial. Someone are using Ethernet, right? Click OK. And then I'm gonna go ahead and download this project. So yeah, and just make sure I'm still connected and go ahead and download to IP12, downloaded it. Click OK. So now I'm gonna download it. Let me go to monitor mode. And then I'm gonna go to PID monitor. That, what I told you was, let me put it here so you can see it. Just gonna do it here a little bit. Okay, guys. First of all, it's your PID loop. If you want, I'm in auto tune already, auto mode. Sorry, not auto tune. I'll talk about auto tune in a second. But I can come here. You can choose a color for your process variable, your set point. Let me repeat this. So I'm in monitor mode. While you go to monitor, which we did the first 3 days. If I go in monitor mode in the monitor box, if I click, I can click on PID monitor. It gives you this PID monitor, right? So now let me go to the I can go here if you want. I was telling you, you can go ahead and change the you can go to the process variable, right? And then change the color of the process variable, the set points, and the PID output as well, right? And then you can tell what you want your limit to be you want your limit to be between, let's say, 0 to 120. You can auto scale it as well if you want, right? And then one more thing I want to do here is I can switch, I can change this parameter. Let's say I'm going to go to, I can go to 10 and then hit, I can change the, let me make sure this is the PIDD going to 4016. Make sure everything we did here is correct. We initialized it. We have M4000, we have set point, the 8 point, okay. And then you can switch, let me go over there. We can switch from mode to mode and go to manual mode. In manual mode, I can basically put any output I want. In manual mode, I can say, I want you to run at 50% output, right? So basically, manual mode, I control the output, right? So I can say, I can, again, to switch between mode, I can go here, say I want to go to manual mode, I don't have a cascade setup. I can go to auto cascade or basically, you know what, guys, I think, let's see, let's go ahead and switch to auto, back to auto mode, right? Let me see what happened to auto mode. So now, sorry. So let me put this in a second, let you look at it for a second, right? Again, in here, the PID taking the PID taking my PID output, which is 0 to 100% decimal, and it's converting it to an SSR, right? Or to a digital output to make sure that the PID output and to make sure that set point and the process variable are equal, right? They don't have any error. So let's go play with change some of the parameter, right? So now if I go to, we go change the set point to 79. So I click on set point, change to 79, and hit send or hit the percentage bar. So now when I change to 79, the PID output said, I don't need any more heat, right? It said that it doesn't, I don't need any more heat, correct? So it's almost went to 0. So now if I go back to, let's see, to set point, go to 84, I go to 84, or let me go to 85 actually, 86 maybe. Now guys, you see how fast I went to 100%? Because I think the KP is way too hard. I'm gonna go back to 2.5 now. And then now it took at 2.5, I'm at 86. It said the error is 86 minus 83, the 3-degree error. I'm at 100% up. But let's see when the heater is heating, right, guys? The heater is coming on. So the heater is almost on all the time, right? To drive the temperature up. Let me go back to lower it to 85, maybe get a little closer. Because this is a small heater. Now notice, guys, I can lower the integral reset a little bit too to go to 6. So now it's gonna getting closer to the set point, right? You can see that, right? So again, it shows you the red and green set point, right? It shows you the set point and process variable, that's the red and green. You want to see as straight line as you could. Really, ideally, you want to have a straight line possible for the best possible output, right, guys? So when you let it run, you really, hopefully, it figured out to be within. I'm within half a degree, right? You guys agree? I'm within a degree, really, of fluctuating between half to 1 degree difference between the measured value process variable desired and the desired output, right? Desired basically PID set points. And then, so let's go ahead and play with this a little bit more. Go back to 79 and then hit send. You have to hit the send command or hit this percentage bar. And notice by going to, it's dumping the heat, but it's slower because you have, remember, it's kind of, whatever goes high up high. If I, let me go back to 85. Let me show you this. I'm gonna go back to 85. And now I want to increase the gain, guys, to 20. And I'll show you how fast you don't want a very high gain. Remember, the gain gets multiplied by error, and it's very large. Let's say if I go to 20 gain, look at that, 20 gain, right? And then I drop it to 79, look what happened. Look how it dumps the output right away. Look at, do you see how fast it dumped the output? You don't want to loop like that. This is where your gain cannot, I always recommend to be about 2 to 3, 2.5 to 3 or something. Because whatever goes high, look how fast it dropped here, right? Versus here, I mean, you want a gradual. So let me go back to 85 and then let it sit there for and see how it's gonna adjust. So let me explain one more thing that I think that so the PIDD is taking my analog output value, the PIDD output or the manipulated variable, this number, which is 0 to 100%, and it's decimal, right, or floating value. It's taking that value and it's converting it into an SSR, in a digital output. And in that digital output, guys, let me show you in the other project, while this is still running, I don't want to interrupt that. I want to show you one more time, really quick, where it is, the digital output, right, is a PIDD digital output. So it's taking the 0 to 100%. I'm going to show you this one again. It's taking the 0 to 100% and converting it to a digital value that, like, and then you can do the duty cycle, anything you want from 0.1. I left the IDEC shows the default of 3, the control period or duty cycle. I can go to any other number if you want a quicker or slower reaction. I mean, for the duty cycle. So right now, what happened, guys? What happened in this case? The PIDD is taking the digital, the PID output, which is 0 to 100%, 0 to 100% decimal value, converting it to on-off, to maintain set point. Look at the fluctuation, guys, of the PID output in order to maintain set point. That's what you want. You don't want fast drop and fast rise, guys. You want to do gradual incremental increase in the PID output instead of or way low. That's the most important part. I cannot stress this enough, guys. And this only is achieved when you have reasonable, not very aggressive gain and integral and so forth. You have to have reasonable number. And notice now in the past, what, from 400 second to almost 600 second, it's only for 3 minutes, guys. Look at that. I'm getting perfect PID control, and the output is going fluctuating to make sure I'm within half a degree of my PID output. So I'll let it run to go to see if there are any questions. I know, guys, really 1 hour is not enough, but I was told I have to stick to schedule. Now, I think that if people want to stick around for Q&A, question and answer, if you have question, please type it in the, I should have said that before, but I'm sure you guys know that, you do that for a living, so you probably know that. So I'll go look at the question in a second. But before I do that, guys, everybody wondering about the auto-tuning. So IDEC is in beta version, in beta testing of auto-tuning. We already have the algorithm written. and we expect to have auto-tuning for the PIDD accomplished. I want to say safely by, well, given what's happening around us, guys, I want to safely say around September. They said June, July. I want to say September, given if we all make it out alive from this vicious virus, guys. I hope you all staying safe, by the way. Anyway, so we will have auto-tuning. We already have it. Is in beta testing. We'll have it available to you most definitely around the summertime. September is the safest bet. Right now, you can run in manual mode and in auto mode, but you have to tune it yourself. We would love to help you. We've had tremendous success with this PID, tremendous success in the way on various applications, from pumping to oil and gas to heating application. We had tremendous success with it. Anyway, I'm gonna go ahead and I'll go to the question, see what kind of if somebody has. Let me go to the questions and see if let's see. Okay, so see if it's a question. I can't see the question. Hey, Britt, are you still on the call? I apologize. Because today we had, okay, so let's see the first question. I don't see the full question. From first question, is the fan working when your SP was 79 degree and the MV was 0? I think when I turned it on, I probably it was not initialized. I think something was kind of wrong. So let me repeat this. Is your fan working when your set point is 79 and the MV was 0? The MV was 0. The fan, what was the set point? I didn't. No, okay. Let me see. Temperature in the box was not changing. Actually, the heater does not see. And okay, let me see. Now okay, it's a fan. Okay, I think I got it now, guys. Okay, the first question I'll go over is the fan working? Somebody was asking when the SP was 79 and the MV was 0. I don't think it was working. Something was weird happening, guys, honestly. Temperature in the box, actually, the heater does not seem to be working. When I turned it on, the first thing, something really weird happened, guys. But as you can see right now, everything's happening. Again, let me demo this. If I go to 79, 78, 77, if I go to 75 degree or 70 degree, and then notice I start to lose in output because right now the heater is the PID output going to the heater. The PID output is 0, means the fan is on. Let me show you then. The fan is on all the time. So if I go to show you this, if I show you the output, you can see the Q4 is the fan, cooling fan is on all the time, guys, because the PID output is on, right? The cooling fan is on all the time. So back to the if the fan working on the SP was 79, the MP was 0. The NV was 0. Yes, thank you. The fan is because, guys, again, I could create the load myself manually, but what I did, I let the I let the fan all the time. It doesn't matter really because yes, the fan was working all the time. Let me go to the second question. Let me see. Are there any limitation, like instruction limitation, for the analog output card versus the PID module? Is auto-tuning the only difference? Is auto-tuning the only? Okay. Second question was, are there any limitation, like there are 32 limitation the PIDD? I think that's a question. Are there limitation like instruction? There are 32 PIDD instruction, guys, for the analog output. Of course, no, the output card, your PV, your PV may be coming from a Modbus signal or something. The limitation and the PID of 32 algorithm. Let me go to the third question. Let's see, next question. As I said, auto-tuning, we don't have auto-tuning now, we will. Okay, does PIDA work? PIDA work? Does auto-tune work in the PIDA? The answer is yes. Now, I have to, you know, guys, to qualify this a little bit. Unfortunately, the PIDA algorithm, we had a little bit of, it was rewritten, it was better, and that was something that it's certain application where we could not control the winding very well. But the answer is yes. Auto-tune works in the PIDA. The answer is yes. As the session begins. Hello. How do you convert FC6A to FC6A plus using this? Assume that you can move a value. Change the set points. Okay, you can move the guys. So the set point, and okay, let me show you this. Everything you see here is written to a data register, right? Let me answer this question. And I apologize, I don't see the question. I see part of the question for some strange reason, right? Britt, I guess answered some of those questions. Sorry, Britt, I can't read like you. But guys, really quick, couple of things. Somebody asking about like changing any of the parameter or the remote set point or the set point itself can be changed remotely by writing to the, for instance, if you want to change your lower and upper range value, you can go right to the 4022 and 4024. If you want to change from an HMI or from an app, if you want to change your set point high and low, you can write to the 4026 and the 4028. All these are available to you. And then you can write to the set point. You can change the set point limit. You can write to the set point. You can change the control action by turning the corresponding memory bit one on if you want a manual. You write to 4001 if you want to run in auto. So all these parameters you can change on the fly, basically by writing to the corresponding register, guys. What you have, right? So Brett, by the way, I wish if I don't have access to, I mean, I see the question in that small window for some reason. I can't see the question. Okay, this is another question. Let's see, another question. I assume that you can move value into, yes, you can, absolutely. Let's see what's next. I just showed you that. You can move value to anything except the PID output. Well, you can move the value to the PID output if you are running in a, you know what? Okay, let me go back to 90 degree because that fan is driving me nuts. Okay, so sorry guys. Okay, so I'm half deaf, so I'm used to the noise. So it's like, wow, this is a lot of noise. All right, guys, let me go to this. So you can write to any, you can write to any of the settings, parameter, tuning parameter, set point, low and high, of course. You can write to all that remotely. I noticed demonstration kit. Can PID control motor speed? I would like to adjust feed rate of material through a saw with a variable speed. Yeah, VFD, if you have a VFD, guys, it's beautiful. If you have a VFD, then you simply, let me exit out of here. If you have a PID, like a VFD speed, VFD drive, you don't want to use digital, you want to use analog and load the register into your 4-20. So basically, if you want to read 100%, if your analog card is 0 to 60, so let me show you this. If you have an analog output card, like what you see here, right? Let me show you this to answer this question. Let's say you have well, this analog output card is 0 to 4095, right? So in this case, I would I would match, I would go to the PID output, guys, the PID output, and I say, I want to, in this case, you can use analog output or you can use variable register. I would match 4095. So the PLC, guys, is going to take your PID output, scale it to 0 to 4000, convert it to a digital value, right? So that's your PID output, 0 to 4095, convert it to a digital value, right? And then it'll automatically plug it into your 4 to 20 to control your, that would be your 0 to 10 or 4 to 20 going to your variable frequency drive. This is basically how we would do it. Okay, so now, so basically, if you need motor flow, if the PID is high, it'll ramp your motor high. If it's low, it'll ramp your motor lower, and so on. Okay, is the TC in the box, temperature control in the box? Yes, the answer is yes. That the K-type thermocouple, the thermocouple is inside. For those of you who also, that TC is inside this box, the K-type thermocouple probe inside the box. The cooling fan is cooling the box from the outside, and the so the heater, the fan, and the heater, the fan, and the probe are always all of them inside this box, like 5 inches by 4 inches by 6 inches. This is why I have to induce heat, guys, because otherwise it'd be really tough to kind of create a real life application, right? Okay, back to what next question. Okay, like in the monitor pop up. Okay, great, thank you guys. The monitor is really nice and helpful. More audio issues seem to be just Elias internet connection. Okay, wow. So I still had some issues. Needs to do audio via telephone. So I was, I guess, cutting out today too. PID was not activating because your cell phones. Okay, guys, thank you for catching that. Yeah, my cell phone was 0. I think I did not pay attention. PID, please explain the control period. I think I already went over that for the PID output. So the control period, guys, basically is, let me go over that one more time. So basically, guys, the control period is the code is taking my PID output 0 to 100% and converting it to a like an SSR, which is right now the 3. So it's almost like duty cycle of 3, basically. So if I'm think about like that, if I'm at 100%, right? If you have a 3, that means it's gonna be 3. The heater will be 3 seconds on, 0 second off, right? If I am at 2, let's go to 2 duty cycle. If I'm 100% PID output, I'm gonna be so basically actually the if I'm let's go let me stay to 3 and go. If I'm 75% PID output, will be 3/4. So it will be 2 sec. Let me see. Actually, 66.67% on. The rest is off. The 32% is off. So I think usually I put 10. To be honest with you, Chris, I use. Let me go outside and come back and put 10. That's the best way I explain it to you. 10. So if I'm at 10 is easy number. It's a decimal number. If I'm at 72% PID output, if my PID output is 72%, then I'm gonna be 7.2 second on and 2.8 second off. Basically, this is how that works because I'm pulsing the PID output. Now, if the minute you change it, it changes with you. But let's say again, so you can increase and decrease the duty cycle. That's what this is. Let's stay here. Let's see what else. Please add the device allocation button to the. Yes, thank you guys. We already asked for the device allocation. So right now, unless I come here, well, I can open it right now. Unless I come here, guys, I don't know what is what, right? Unless I come here, I don't know what. So it's gonna be a button in the next version where you add the device allocation. Thank you. Good, great question. That's already done. That is useful. Absolutely agree with you. M8416 output, is this a pulse output where the PID-MV control determine pulse? Yes, the answer is yes. And I already explained that question. There seemed to be a time term. Was it a function? A time term? No, the time term, I'm assuming the guy left. Time term, I'm assuming the that's for the PID output. I'm assuming for the duty cycle. That's what the duty cycle is for. What is the function? I think I already answered that question too. Why did we use KD derivative? Because I mean I use very little derivative, guys. As you can see, I used the by the way, I'm at 100%. I'm almost at 87 degree. I mean, I'm almost getting there, right? The fan is off, and so I use very little derivative because in this case, guys, the derivative helps you with anticipating the error, right? In this PID, it does not really help me so much. So I stayed with very low derivative. Okay. I think that's are all the questions I had. I apologize if I'll try to call in again. I did not think. I tested it. It's supposed to be good, but anyway, guys, I'll try to work on the audio for the 2 p.m. Eastern Time session. Thank you so much for your time and for attending our GoToWebinar this morning. I'll repeat this session, hopefully with a better audio at 2 p.m. Eastern Standard Time. Have a great day. Please stay tuned to future webinar on programming the IDAC FC6A. Thank you so much. Have a wonderful day, everybody. Bye.